Okay, guys, what do we think the first one is? Yeah, decomposition, excellent. So what we'll do is we'll just put a tick in that box. Okay, what about the second one? The second one's a bit confusing because the states are not there. Let me put the states in and then see if that helps. Okay, I don't know if you guys can see what I'm writing here. Sorry. And this isn't this. Okay, so if all of the other products and reactants are aqueous and only one of the products is a solid, what type of reaction is that? Yeah, precipitation, excellent, good work. So that's precipitation. What about the third one now? So we've got 2 hydrogen gas atoms plus 1 oxygen gas leading to 2 molecules of water. What type of equation would that be? Yes, the states will be included in the test. So if we give you a precipitation reaction and ask you to classify that, then the states will be included. If they're not included, then you need to kind of use your precipitation table to basically determine that. Okay, so with this third one here, with part C, sorry, this can be defined as either 2. So if we were to give you this option C in the actual test, the answer would either be synthesis, which is not in this list, but we could add it there, or it could be neutralization, it could be combustion. Okay, so it could be either of those, okay, because we've got this production of water and oxygen gas there involved. Again, if this was in the test, we wouldn't give this only a 1 answer. So I think most of you in the chat mentioned that this was synthesis, which would be correct. But I don't know why there's not a box here for synthesis. Okay, what about the next one? What do we think the next one is? We've got the formation of a metal salt and water. So a metal salt and water, and the reactants are an acid, okay, nitric acid plus a metal oxide, which is potassium oxide. Yeah, neutralization, exactly, because neutralization is when we've got the products being a metal salt and water, okay? What about the next one? Okay, the next one can be related to one of the options that's not actually listed here. Can be synthesis or combustion, again, because we've got the formation of that oxygen gas there. So it can be either combustion or it can be synthesis. In fact, I'll probably put an S next to the ones that were also synthesis. Okay, what about F? So what would we classify that one as? Decomposition, yeah, excellent. So decomposition would be the correct answer there. Okay, sorry, this one. All righty, what about the next one? And you might need the states for the next one, but without the states, think about what this could be. So you've got obviously some reactants there and you've got some products that are forming. If I was to write the states for you guys, just to give you a little clue, that should say AQ. AQ, and this would be S. This would be AQ. So everything else is aqueous, and there's only one solid product in there, or one insoluble product. Yeah, precipitation, excellent. Okay, it's precipitation because we've only got one solid product in there. Now with precipitation reactions, it's good to just always check back with your solubility chart to make sure that you can see whether a solid substance will form. Okay, in this case, lead iodide will form the solid substance because it's insoluble. These elements tend to be insoluble, whereas nitrates generally don't form precipitates because they tend to be soluble. Okay, it's also important to remember, guys, what does this word actually mean? When I say aqueous, what does aqueous mean? We know that solid means that it's a solid state, that it's, you know, like chunk, or that it leaves behind like basically, you know, insoluble kind of undissolvable precipitate there. But what is aqueous? What is AQ? Not exactly liquid. AQ means aqueous, which is related to water. It's related to this idea that something is dissolved in solution. So what that means is that, for example, and I'll just write that first, dissolved in solution. What that means is that when I have, for example, an aqueous compound, such as in this case, let's say potassium nitrate, okay, potassium nitrate, if I take potassium nitrate and put it in a test tube, it will completely dissolve in solution. Okay, it'll be completely dissolved and you won't be able to see it anymore. It's not going to leave behind any mark. It's not going to leave behind any cloudiness or any gel-like substance in the test tube. It will completely dissolve and it will look like water from the outside. So that's how you can remember that any compound that is aqueous is not water, but it looks like water because it's completely dissolved in that solution. When you've put it into the test tube, it's completely dissolved in that solution there. Okay, that's what aqueous means. It's important to know that because it helps you to understand what precipitation reactions are and how they work. All right, so let me just get rid of some of those scribbles. Actually, no, it's all right. Okay, what about H, guys? What do we think H is? So again, you've got the formation of magnesium sulfate. Okay, sulfuric acid plus magnesium hydroxide gives us magnesium sulfate, which is a type of metal salt, and water. So what was the name of the reaction where a metal salt and water is produced? Does anyone remember? Yeah, neutralization. Excellent. Okay, so neutralization is the name of the reaction where you've got a metal salt and water being produced there. Okay, what about the next one? I think the next one's actually pretty easy there. Methane plus oxygen gives us carbon dioxide and water. So there's only one reaction where carbon dioxide and water are the clear products. Does anyone remember what that reaction is? Yeah, combustion. Excellent. So combustion is when we're burning fuel, and that's when we've got a lot of carbon dioxide gas as well as water vapor that comes out of that. So combustion is the answer for that one. What about the next one? So J, so barium chloride plus sodium sulfate gives us barium sulfate plus sodium chloride. What do we think that one is? Again, here you've got some clear, what's it called? Here you've got some, I'll put some states there for you guys to get you started. So everything else is aqueous and only one is solid. There's only one solid undissolvable substance in the products. What's the name of that reaction? Yeah, precipitation. Okay, so precipitation, everything else is aqueous, but we've got one of the products, could either be the first product or the second product, that is solid. It's an undissolvable solid substance there. Okay, it's left behind in the test tube. So remember those videos we watched where, for example, with the lead iodide, it was like a yellow kind of jelly substance that was left behind in the test tube. That is basically the precipitate. It's not dissolved, and so it remains in solid state. Okay, so now we've got part K, or question letter K. What do we think that reaction is, guys? It's a pretty easy one, I think. A bigger compound breaking down into its individual atoms or individual molecules there. Decomposition, yeah, excellent. So that's decomposition. And then sodium hydroxide plus hydrochloric acid gives us sodium chloride plus water. So that's a metal salt and a water. So what's the name of the reaction given to? Given when there's a metal salt and water as the products? Yeah, neutralization. Excellent. Good work. So that's basically the different types of reactions. And I think this worksheet is more towards your actual like year 10 kind of level. Okay. I think the other worksheet, we just got that worksheet from the internet and modified it a bit. So that worksheet was a little more, maybe could have been more advanced. So if you guys understand what's kind of on this slide, this is the basics, or this is kind of like what we would expect, more clear-cut kind of examples. Okay, so that's how you basically classify equations. Okay, and remember the main way in which we decide, is it decomposition, is it precipitation, neutralization, combustion, or synthesis, is by understanding what each of those chemical reactions typically are. Okay, in synthesis, you're adding, remember A plus B, there's an addition. In decomposition, it's like you're breaking it down. So AB breaks down into A plus B. Okay. In precipitation, we've got an equation where everything else is in aqueous state, and there's one product that is a solid. Okay. That's what a precipitation reaction is. It's characterized by the formation of a solid and undissolvable precipitate. Okay, as one of the products there on the right-hand side. And neutralization reactions are basically reactions that involve the formation of a metal salt. So in this case, when sodium hydroxide and hydrochloric acid, when that acid and that metal oxide combine together, we have the formation of a metal salt, which is sodium chloride. and we have the formation of water. Okay, so a metal, salt, and water is what neutralization is about. Those are the two products that you can kind of predict or determine when you get a neutralization reaction there. And the last one is combustion. And in most of our examples that we've gone through with combustion, particularly with combustion of hydrocarbons, the main kind of products that we see there are carbon dioxide and water. So if you get any equation that's got carbon dioxide and water as the products on the right-hand side of the arrow, then you know automatically that that is a combustion reaction. Okay, any questions, guys, about classifying equations or the types of equations? I know this is actually quite a hard or difficult topic because it's easy to get confused between the different types of equations. But as long as you, like I've recapped it very quickly here now, but as long as you just go back and recap and distinguish, maybe even make a concept map or make a table where you're clearly differentiating between the types of equations and put a few examples in there, maybe from this worksheet, you should be able to differentiate between them. Okay. So that's the basic idea. So I'm hoping that everyone is okay because I haven't got any other extra questions about this specific classification part. So what we might do is we might actually move on. In fact, are there any other things that I've missed? I think I already talked about the first page in the first few minutes of today. Basically, guys, you need to know how to do your chemical symbols. Some of you are really good at this now. You're really good at writing chemical symbols, but it's important that you make sure you write them correctly, particularly when you're writing equations. You need to be able to, for example, write magnesium chloride correctly or potassium chloride correctly. And remember, it's all about doing the crisscross and swapping the valency numbers there. Okay, that's how we write the equation. When you're looking for the ions, okay, or if you need help with the ions and you don't know which number is associated with sodium, use your valency table. That's the reason we give it to you. Some of you in the last test made mistakes that could have been easily avoided if you just went back and looked at your valency table. I know it can be annoying going back and forth, but it might save you a mark or two. So use your valency table because it tells you, literally gives you, okay, sodium is Na+. It tells you that chlorine is negative. It tells you that aluminium is 3+, okay? All that information is given to you there. And, you know, you're given your periodic table as well. So you shouldn't lose marks for simple questions that involve things like ions. Okay, so just reminding you guys that when it says ion, remember you need to put the charge there. Don't just write the chemical symbol from the periodic table. You won't get any marks. You need to put the relevant valency or the relevant charge as well. Okay, so classification is probably covered. This is just some scenarios, guys. You can probably just do this kind of on your own, and then when I publish when I upload the answers to this later today, you can kind of check your answers there. These are just scenarios which are good to go through and good to understand the different types of reactions. Now, we haven't actually done respiration, so you don't need to worry about that, but the others we have done, so you can have a look at that. I just want to see what other stuff there are. Even with this question, the rate of reaction, we learned about rate of reactions and a few examples. For example, we know when we're baking a cake, the rate of reaction tends to be increased. We want to increase the rate of reaction because if the oven is not turned on at enough heat, for example, the cake won't bake. It will just simply kind of, kind of stay there, and it won't really, that baking process won't occur. Okay, so we need to increase the rate of that reaction by increasing the heat. Okay, if you bake a cake at 100 degrees, when the recipe says it's supposed to be baked at 180, the rate of reaction is not going to be, it's not going to be hot enough. The temperature is not going to be hot enough to actually increase the rate of reaction. Okay, and we talked about the effect of temperature on the rate of reaction. Okay, other things, for example, medication. When you take Panadol or something to relieve a headache, you're increasing the rate of reaction of that particular medication so that it can work quickly. Okay, in some other aspects, like for example, with certain things like fireworks, we talked about the fact that with fireworks, we don't want the reaction to be too fast because we want to still be able to control that. We don't want it to get out of control and potentially cause harm or danger to others. Okay, so certain functions or certain examples in real life require the reaction rate to be increased. Certain reactions require the reaction rate to be decreased. Okay, it's just knowing those real life examples there. And we talked about a few of these when we did this spread as well with rate of reactions. Okay, so whoops, if we go further down. Okay, we're looking at some chemical balancing of chemical equations here. So with this one, it just kind of breaks it down for you. There's nothing, you know how we usually do it like side by side, but they've just put it all in one lot. So usually we put down like C equals this, H equals, like we put one on the right hand side, one on the left hand side. All these guys have done in this worksheet is they've put it all in one go. Okay, it's the same thing, the same process that we would normally use, but what they've done is they've just formatted or set that out a little differently. So yeah, this is just about balancing equations. Does anyone have any issues with balancing equations? I know we have done quite a bit of balancing equations, but like in general, like, are there any confusions in terms of the steps involved? Or do you guys want to maybe try a sample question, another sample question? Like, what do you guys think? Oops. Let me just see what other questions we have in here. Yeah, these are all balancing equations. And look, sometimes we give you the equation and we just ask you to maybe fill in one or two coefficients there. Sometimes we might give you one coefficient. For example, in this question here, they've given you one of the coefficients and you've just got to fill in the missing one there. So sometimes we don't ask you to balance the whole equation. We might only ask you to balance a part of the equation or just half of it. So just keep that in mind when you are doing balancing equation questions there. Okay, literacy review is just filling in the blanks. So this is a really good fill in the blanks activity to do, guys, just to revise your knowledge of the theory related things. Some of these are not going to be super relevant to us, like terms like agitation, catalytic combustion. Oh no, catalytic combustion should be okay, but agitation, some of the words might not be relevant to us. If it's not, then just leave it out and don't worry about that. And then some precipitation reactions. We did a few examples of precipitation reactions as well on Friday, and we wrote some of the ionic equations and the spectator ions. Does anyone have any confusions with reference to writing like ionic equations or spectator ions, or don't know how to do that, or just let me know? Yes. So if you have a question, yeah, just let me know. Will I be teaching psych next term to you? Yes, I will be teaching psych. Yeah, I'll be a teacher for the whole semester. So you will be stuck with me until the end of the year. Yes, so I will be teaching you psych, and I am looking very much forward to that as well. Okay, for precipitation reaction, formula AB plus CD is AD, doesn't matter. Oh yeah, good question. So no, so a question was for precipitation reactions, and I'll just put this formula down so everyone can understand what the question is. So remember, guys, when we talked about precipitation reactions, we said that AB plus CD is AD plus CB, okay? We said that was the general formula. So the question was, does it matter if AD comes first in your precipitation reaction, or does it matter if CB comes? No, it doesn't matter. So in the equation, in your answer, if you put the precipitate first in your answer and the other aqueous product second, it doesn't matter. It doesn't matter about the order of the actual products, okay? As long as both products are correctly named and have the correct states, that's all that matters to us. It doesn't matter which one comes first or which one comes second. So you'd still get the mark there as long as everything else was correct. Another really important thing to mention, guys, is that when we're talking about aqueous solutions and solid solutions or solid states with precipitate reactions, you need to be really careful to make sure you always write down the states. Okay, if you don't write, for example, aqueous, aqueous, solid, aqueous, and let's say that equation was worth 2 marks, you automatically lose 1 mark. So you only get 1 mark out of 2. Okay, even just because you've missed out on writing those little brackets with the states in them. And this goes for any equation in chemistry. You need to write down the states. Otherwise, it's not a complete or full equation. Okay. I don't have precipitation reactions, writing them out. Okay, we'll do maybe one precipitation reaction then, and I'll just show you guys. We'll just recap that, how to do that. Okay, let me just go down. Where was the precipitation reactions? Okay, let's try the first one. So aqueous solutions of potassium iodide. Yep, I'll go over the spectator ions as well. We'll go over the spectator ions for this one, the first question, because I think the question anyway asks us to write the ionic equation and spectator ions. So just remember, when we're writing the I guess the hardest bit of writing any equation is the chemical formulas. That's what you need to get correct. So just remember that potassium iodide, okay? When it says aqueous solutions of potassium iodide and silver nitrate are mixed, that means that these two are our reactants, okay? So we write them down on the left-hand side of the arrow. Okay, so this will be the equation for, or the chemical formula for potassium iodide, and then silver nitrate will be Ag. Now, if you go into your polyatomic ions valency table, you'll have formulas for all the polyatomic ions. And from there, you'll be able to see that nitrate has a formula of NO3. Okay, it's going to be AgNO3. And I'll talk about how we came to these, how we got these kind of chemical formulas. And I'll put the arrow, okay? I know that these are my reactants. They're on the left-hand side of the arrow. How did I come up with potassium iodide? How did this worded formula turn into this chemical formula? Basically, when you look at the charges, potassium, we know generally tends to have a +1 charge. Okay, it's in group 1 of our periodic table. It has a +1 charge. +1 plus, it's the same thing. On the other hand, iodine generally has a -1 charge, because remember, iodine is in the same group as chlorine and fluorine and all the other kind of halogen type nonmetals there. So when we basically swap these two, or we do the little crisscross thing, what happens is, because they have the same number, the net charge will be 0. So basically, all we're going to write is Ki. Okay. Now, this would be different if, for example, let's say just hypothetically, if potassium had a charge of 2 instead of 1, this would then be Ki2, because then iodine takes on the 2 from potassium. But obviously, we know that that's not correct, because we know that potassium has a charge of +1. So we'll leave it like that. Okay, that's how we got potassium iodide as the formula there. Silver nitrate, how we got the formula is, we know that nitrate has a -1 charge, okay, for the polyatomic ion. You can find that using your valency table. And we know that silver, which you can also find using your valency table, has a +1 charge. So when these two kind of crisscross, you'll notice that +1 and this is -1. So the charges will basically equal to 0. The net charge will be 0. And this is how you would write the formula. Okay, that 3 is from the original 3 in nitrate. That's not something that's gained. That was there from the beginning. So that's how we get the formula for silver nitrate. All right, if you're not following so far, or there's something that hasn't made sense so far, just let me know. Now, we know that in a precipitation reaction, that both of these will be aqueous. Okay, we don't even have to think about it. We know that both potassium iodide and silver nitrate will be aqueous solutions, which means if I put potassium iodide or silver nitrate into a test tube, they will basically dissolve in that water, or they'll dissolve in that solution, okay? And the question also tells us that they're aqueous, but we know that they're aqueous even if the question didn't tell us. Now let's look at the actual products that are formed. We know that the formula for, and I write it here, we know that the formula for precipitation reactions is AB plus CD gives us AD plus CB. Okay, so we know that that's the general formula, okay? And we know that in this, all of them are aqueous except one. Okay, and that's one of them is usually the precipitate there, the undissolved solid substance that's left behind. Okay, so now when we look at this, if we're going to name these out, or if we're going to classify these now, okay, potassium is the A, iodide is the B, silver is the C, nitrate is the D. Okay, so now all we're doing is we're matching this up. So we know that for example, we know that our AD is going to be potassium nitrate, or it's going to be one of our products there. So potassium nitrate is going to look like that. Again, we know potassium has a +1 charge, nitrate has a -1 charge. There's not going to be any extra subscripts that we're dealing with here. And then the other product is going to be CB, which is going to be silver iodide. Okay, so if we go silver iodide, again, silver iodide is not going to have any changes in terms of the charges, because silver has a +1 charge and iodine has a -1 charge. The overall net charge will be 0. Okay, now here, how do you determine which one is going to form the precipitate? It's not always in the same position. Okay, some of you, when you were doing your worksheet and you answered this incorrectly because you automatically assume that AD will always be in this position. Like that question I answered before, it won't always be in the same position. And this is where you need to open up your solubility chart and have a look at the actual solubility chart. So let me have a look if I can just quickly bring that up here and then just show you guys what I mean. 4.5. Okay, I just want to show you guys. And this is the same one from the book that we're going to be using as well. Okay, now how do I paste that into this? Okay, what I'm going to do is I'm just going to send, no, not send. Okay, if you guys have access to your precipitation or your solubility chart, if you've got that handy, basically what that looks like is you've got the 3 columns. Okay, you've got the 3 columns there. And then remember the first column is the soluble column. So that's the basically column where no precipitates are formed. Then you've got the insoluble column in the middle, and that's where precipitates are formed. And then you've got the slightly soluble, but we're not too concerned with that for this question. So in the soluble and insoluble column, one of the compounds or one of the what's it called, polyatomic ions that are basically always soluble or always dissolved in solution are all nitrate. So if you go to your solubility table from 4.5, it says all nitrate salts. Okay. If you look into our products here, we can see that we have potassium nitrate. Potassium nitrate is an all nitrate salt. It falls under that category, which means it's soluble, which means if I write S here, that's wrong because I haven't cross-checked with my solubility chart. So it's actually important for me to acknowledge and read my solubility chart and realize that all nitrate salts, as well as all group 1 elements as well, and you know, potassium is a group 1 element, are soluble. Soluble means they do not form precipitates. That means they can't have the S label or S solid state attached to them. Okay, so that means that I'm going to give my potassium nitrate an AQ, and everything else is AQ. That automatically allows me to assume that silver iodide in this situation is my precipitate that's formed. Okay, and I know that even if I cross-check with my solubility chart, silver iodide is generally a insoluble substance, so it does form the precipitate here. Any confusions so far? That's basically the equation for the first question there. Okay, the precipitation reaction question. Any questions so far? Look, the hardest bit of this is writing the chemical formulas down. The rest of it is pretty straightforward. It's just a matter of cross-checking with your solubility table there. Okay, so what I'm going to do is now we're going to write the ionic equation and spectator ions, and then we'll finish up for today. So when we're looking at the ionic equation, and I'm just writing all over the place here, but when we're looking at the ionic equation, what do we do with the ionic equation, guys? What do we start with? If anyone remembers. So I put the arrow. What's my product for my ionic equation? I'm dealing with one of these. Am I dealing with one of the aqueous solutions or the precipitate for the ionic equation? Yeah, we're dealing with the precipitate. Okay, so what I do is I take my precipitate, which is silver iodide. I put it here, just like that. I put down that it's solid or that it's in precipitate form. Okay, and then I work backwards. Okay, that's what we do in the ionic equation. We state what our precipitate is, and then we work backwards. Okay, how are we going to work backwards here? We're basically going to write down the individual ions that make up silver iodide. Okay, so I know that silver is one of them. So I'm going to Ag. Now, does anyone remember what charge does silver have? Anyone remember what charge does silver have? Is it +2, +3, +1? What is it? Okay, it's going to be +1. So you're going to write plus there. And that's obviously in aqueous format because there's an individual ion that's dissolved in solution. And then you put a plus sign in the middle, okay, because it's an ionic equation. And any equation in the reactants, you're just adding them together. Okay, and then the next one will be, what's the second element that's in our precipitate? Silver iodide, right? So iodine is the second one. So we write I. Now, does anyone remember what was the charge or what was the valency on iodine or iodide there? Yeah, -1. Excellent. You can see that from here when we compared the two. Yeah, it's -1. We just put a negative there. The same thing, this as an individual ion, this is aqueous in solution. It only becomes a precipitate when it combines together. So these two individual ions started as individual in aqueous state. When they combined together, they became different in terms of their state. They formed a precipitate and thus took on a solid state of matter. Okay, so that's the ionic equation. Okay, and the last step is the spectator ion. So when we're looking at the spectator ions, we're basically going back to our precipitation reaction here and looking at everything that wasn't involved in the formation of the precipitate there from the reactants. Okay, so we look at this, we know that our precipitate is silver iodide. So we cross out silver, we cross out iodine. Okay, and the two spectator ions that we have are potassium. Okay, spectator ions. Just quickly write this up, spectator ions. So we've got potassium as our first one. And remember, because it says spectator ions, we need to write the charges as well. So we've got potassium, and we know that potassium has a K+ charge because it's in group 1. And then we've got nitrate. And we already know the charge of nitrate, which is NO3-. We know this from our valency table there. Okay, that information is given to us in the valency table. All right, so that's basically, again, just going through one precipitation equation there. Okay, and just showing you step by step how it's done. So just try and do a few of the others. And like I said, I'll upload the solutions tonight so you can cross-check your answers. So just give that a go. The more equations you do, the better you'll become at it. Also go back and rewatch some of the older videos we've done on precipitation reactions and some practice questions, and you might be able to refresh your memory as well. So what I'm going to do, guys, is I'm going to stop the recording